We're going to do often what's called a 3N analysis for a molecule. In particular, I've picked one to simplify our first analysis that we're doing here together. HNO, so it is a bent molecule, and HNO a structure that would look like that. It's 3 atoms. The only symmetry that it has is the fact that there's 3 atoms and there's a mirror plane. So it has an identity and has a mirror plane. We're going to do a 3N analysis. And that's where we go, and you'll have to imagine this because I can't draw it exactly on them without making it too messy. Putting a little set of 3 axes on each of the atoms. So you should imagine this on the center of each atom. We've got an X, Y, and a Z coordinate axis. And this is where this name 3N analysis comes from. This will give us the symmetries of the vibrations plus rotations plus translations of the molecule. We will take this and subtract out the rotations and vibrations. We'll see there's a really nice way to do that. And it'll give us the 3N minus 6 vibrations. So we'll be able to figure out the symmetries of the vibrations for this molecule. Okay, so we're going to set this up just like our character table up there, CS. It has an identity and it has a sigma H. And then we're going to see how each of these affects each vector on each one of the atoms. So E doesn't do anything to any of the vectors. So 1, 2, 3, 4, 5, 6, 7, 8, 9, all 9 of the vectors are left totally unchanged. Whereas our mirror plane, so if we call the one that's in the page and up the z-axis, then the molecule is lying in the xy plane. And so the mirror plane would be the xy plane. So what would happen is when we do this reflection, x and y is left alone on each atom, and z goes into the negative of itself. And so what contributes then, so x and y are left unshifted. So from each one of the x's, we get a +1 for a total of 3. From each of the y's, we get a +1 for a total of 3. And then for the z's, z goes into negative z, so we get -1 from each to get a total of -3. So I sum this then to get the total character. 3 plus 3 is 6, -3 is 3. Okay, 9 and 3 is the character of this reducible representation. Well, I have to do some work to do this reducible representation to work it out. It's going to be some number of A prime and A double primes from the character table. And I like to follow the method of the Carter book, where he adds 2 columns and does this, what he calls the worksheet method. So sigma divided by 2. Okay, the sigma, we're going to do a total once we're done, and we're going to divide by 2 because there's a total of 2 symmetry operations, an E and a sigma H. 1 and 1 gives me 2. All right, so what I do is 9 times the one that's here, and then times the one that's up here to follow this method. So 9 times 1 times 1 gives me 9. 3 times 1 times 1 gives me 3. So that gives me a total of 12. 12 divided by 2 gives me 6. This next one now, 9 times 1 times 1, so this one's still 9. 3 times 1 times -1, so this gives me a -3. 9 minus 3 is 6. 6 divided by 2 gives me 3. And this sums up, 6 plus 3 gives me 9. So 9 total motions of the molecule right now. All right, so gamma red, okay, that's for a 3N, is 6A prime plus 3A double prime. Okay, now we go back up here to the character table, and we're going to subtract out. Let's first do the translations. And nicely, this is here in the character table. So translation along X, translation along Y, translation along Z. So 2A primes, 2 of those are translations of the molecule, and 1 of the A double primes is a translation of the molecule. Also, someone has worked out for us the symmetries of the rotations. So rotation about the z-axis is here. So minus A prime, that's a rotation, and then minus 2A double prime for rotation about X, rotation about Y. So this is the minus 6 for the 3N minus 6. So 6 minus 3 leaves me with 3A primes, 3A double prime minus A minus 2A leaves me with no A double primes. So the 3 vibrations of this molecule all have A prime symmetry.